So this algebra lesson is going to look at polynomials and how they represent investing money. When amounts are invested periodically and earn interest over time, the total value can be represented by a polynomial. So let's take a look at an example. Each birthday from age 12 on, Jessica received $500 from her grandparents. She saves the money and it pays a percentage of 6%. How much will she have by the time she's 18? So what the table does is represents how much is earned every single year. So for the 12th birthday, of course, she has $500. It hasn't been invested yet. By the 13th birthday, that $500 has been in the bank earning 6%. So the calculation is 500 times 1.06 plus the 500 she got on her 13th birthday. That pattern continues to the 15th birthday, and you can see the four arrows. Each birthday is represented by a different amount, a different term. And that last $500 is from the 15th birthday, has not been invested yet, giving her $2,187.31. So you can see the pattern. By her 18th birthday, she will have 3 more gifts of 500, because that was the original question, from 12th birthday to 18th. And she'll earn interest on this money for 3 more years. The total will be 7 different terms, all being added together. That first amount got invested for 6 years, all the way until that last amount never got invested yet. That's from her 18th birthday, and she'll have just over $4,100. So she earned $696.91 in interest because she got $3,500 in gifts. So I guess what it's showing is that you don't want to just put money in the bank and keep it there and not add to it. The power of compound interest is, of course, adding to your principal every single year. So letting x equal 1.06, the amount of money she has in dollars after 18th birthday is given by this general polynomial. So if the interest rate was 8%, you'd replace x with 1.08. If the interest rate was 4.5%, you would replace the variable x with 1.045, and you would get a different total. So polynomial in x, that term fits into what I was just showing with that last long polynomial. So the definition is a sum of multiple powers of x. Why is that useful? Well, if the interest rate changes, we substitute a different value of x. We also call that the scale factor, and the scale factor in a problem with investments is the interest rate, but we make sure to write it as a decimal. So if it gives it as 3%, we write 1.03. So in example 1, the scale factor, I need to go back. In example 1, the scale factor was given as 6%, so we would write 1.06. That's the scale factor. Alright, let's look at another example. Rahib's parents give him $100 on his 12th, different amount on his 13th, $120, and then different amounts on the 14th and 15th. So if the question is how much money will he have on his 15th, let's write a polynomial to describe how much money he has. So that first amount, 100, got invested for 3 years. The 13th birthday money got invested for 2 years. The 14th birthday money got invested for 1 year. And the 15th birthday money, $160, hasn't been invested yet. Therefore, there is no scale factor attached to it. So we can represent it as a polynomial with a degree of 3. If the problem said 4%, we would put in for x 1.04 and calculate for a total. What if we added to this a different scenario? In addition to his parents, we have his aunt giving him $50 on each of those birthdays. So we could show this as 2 different polynomials, but you'll notice that we can add like terms and we can write one total polynomial representing the 150 that goes in the bank for 3 years, 170 for 2 years, 190 for 1 year, and then he got $210 on his last birthday, the 160 plus the 50. That's assuming the scale factor is the same. Another term associated here, which would be important, is standard form for a polynomial. That's when you write it in decreasing powers of x. You put the 3 first, then the 2, then the 1, and then the constant at the end. Let's take a look at this example. This is interesting. Every year after they are married, a couple deposits $2,000 into an account that pays 6.5%. So start to think about what you think the scale factor is for that. The couple starts by depositing $2,000 when they are married. How much money will they have saved by their 10th wedding anniversary? Well, I'm going to show you the key sequence here because it's rather lengthy. However, I want to show you what's going on here. We basically have a $2,000 that's going in for 13 years, for 12 years, for 11 years, for 10 years, for 9 years, all the way down to the one on their 10th wedding anniversary. So the way I would represent that is I would put in 2,000, and then I'm going to go ahead and plug in all of the values and take note of the key sequence here and how I'm going to use 1.065 for my scale factor. So follow along with me here, maybe punch it in your calculator as we go through, and then we'll hit enter at the end, and hopefully we'll come up with a number that represents the total. Alright, so it took a lot of work, but I put it all in, as you can tell. Thanks for bearing with me there. $2,000 every year. Notice what the power is of adding principal every year. Now this would be pretty amazing to do this for 10 years. As a family maybe can grow, it's difficult to maybe save that much, but what's going to happen is in 10 years they'll have $30,743.12. And that's if they add $2,000 to that account every single year. So that kind of shows you the power of compound interest with adding amounts throughout the years. And that's it for this presentation. Thanks for watching.